Because I have to start it. And you should have already thought of it. I don't know, by the time I realized that yesterday, that today was today, I did not have time to prepare it. Well, you still have to do this Thursday, you have to have the papers of the span. I knew it. I told you to do yourself. I told you I'm not doing it. Well, there's no way I'm gonna get to today, so.
Just because this always makes its way around the chemistry meeting circuit about once a year.
Take elements made up my copies.
My personal favorite is
I think that carbon is like huge.
yes. I've also seen one of these where they just filled in everything that was added to not skin with carbon. The entire periodic table is just carbon.
Wait, where's that?
Sodium, potassium.
Yeah, very good. Well, yeah, because they're all like named after the schools and stuff. They are, yeah.
Americium and berkelium and californium and.
Very cool. Maybe because
I thought you would appreciate that.
I do.
You could also make them the nukes part of America too,
Yeah.
arguably. All right. This is week 8. This is what we spent our last lecture on before the test. So that's now been a week and a half. So figured we'd start with a little bit of review because I would wager you weren't focusing on this when you were reviewing for the test, which is fair. So reminder of the way these work. It's all tied to what's the best leaving group, which is another way of saying what's the weakest base. The weakest base is going to be the best leaving group because it's the most stable on its own. 8. I know, it's coming up fast.
So the weakest base, the strongest.
It's the best leading group, yeah.
Best.
So that means that if you look at our acid derivatives, they follow the same trend. The most reactive acid derivative is the one that has the best leading group, which is our chloride or our bromide. Then our acid anhydride, because with the acid anhydride, the leaving group is an entire deprotonated acid. So we know that that's relatively stable on its own.
So the weakest base is the best leading group, is the most reactive?
Correct. Because it's easiest to replace on this carbonyl. And remember, these two, this graphic has them with a greater than sign, but they're really approximately equal. We can convert back and forth between esters and carboxylic acids pretty easily just by varying concentration. Which is part of how you make soap and how your body stores energy in the form of triglycerides.
I think those two things, whatever.
So if you look at a triglyceride, glycerin is a so this is glycerin. So it's a triol. It's on 3 carbons. If you take this alcohol and you turn it into 3 esters instead of 3 alcohols, you get the way that our body stores both that all mammals really store excess energy in the form of fats these R groups are just big long chains of CH2s. So they vary in length a little bit, but it's usually be like CH217, CH3, or CH214 and a CH3. So this is what a triglyceride is, but it's really just 3 esters. You take this and you expose it to a strong acid or a strong base in the presence of water, it turns back to being glycerin and a whole bunch of just fatty acid chains. And those fatty acid chains are, you remember the term amphiphilic?
No.
So amphiphilic, break it down from the Latin. Close?
Would that be water? Water?
No. Water and land, 2 things, right? Amphi means both.
Okay.
Like ambidextrous, it's the same root as ambidextrous. And philic means loving, like hydrophilic. So amphiphilic means it's a molecule that has where part of it is hydrophobic and part of it's hydrophilic. So if you have a long fatty acid chain,
So wait, it means loving.
yes. It's the opposite of phobic. So if you have this fatty acid, or if you have this deprotonated carboxylic acid, and then you have a whole bunch of CH2s and the CH3, you get this big long molecule where part of it, not just polar, it's charged. And part of it is completely non-polar.
So part of it, would it also be like water? Right?
So exactly, as part of its polar, it's hydrophilic.
What's the polar side?
Yeah, so this is hydrophilic, water loving. I don't remember if there's 2 L's or not, doesn't matter. But then this whole portion over here is hydrophobic.
Instead of calling it water, loving, like,
Water bearing would be the Latin translation.
I think I've probably did it for it.
Yeah, same root.
And
It's-
it's non-polar.
And non-polar. Right, hydrophobic and non-polar are synonyms. So what this does, reason that this gets is really useful to us. So for one, we make these fatty acid chains and we turn them from being this triglyceride. This triglyceride's not really going to be very polar at all. Like the ester group is a little bit polar, but the main part of this molecule is going to be pretty hydrophobic. You take it and you expose it to acid or base and let it react in the presence of water, you're going to get 3 of these. And then there's glycerin left over. If you have something that's amphiphilic, what naturally happens is it'll set itself up so that and I say it's setting itself up, we know it's really just following delta G. But you wind up with, I'm going to use a little circle for the hydrophilic piece, and then a little tail for the
Which part is?
the tail is the hydrophobic piece. So we put a negative charge on each piece to make it clear that that's the piece. So it does this, it'll naturally set itself up so that there's these little bubbles called micelles. It was a big health trend a couple months ago on TikTok and stuff, micellar water and that kind of thing. Micellar water just means it has some soap in it, basically.
I use to measure my finger off.
It works. It's basically just a solution that's pre-made with water and soap together. So when you put soap in water, it does this. in that it's really effective at cleaning things because the stuff that you can't remove with water usually will dissolve in a hydrophobic solvent. And so this basically creates little bubbles of hydrophobic area in water that the dirt or makeup or whatever gets dissolved in.
Yeah.
And then gets washed off and carried away. It is. Fun fact, this is also one of the best guesses for how life first arose. Because if you take these chemicals, so we know DNA will all automatically replicate itself, right? Even in the absence of a cell, we did that with PCR with Science Club, right? You did.
I've never got one of the rabbit answers.
It's true.
Still waiting.
Your abnormalities throughout the whole process. So we know that DNA and RNA will replicate themselves just with the right chemicals floating around, but they're not really protected very well. One of the first types of, if you could even call it life, one of the first things that allowed RNA to be protected so that it could continue to self-replicate was if you had just a strand of RNA that got buried in the middle of one of these micelles. It's now protected from the aquatic environment that has all these harsh acids, bases, things like that. So they called it a micelle with RNA basically buried inside of it. They call it a protocell.
Words.
So many words. You don't need to take notes on this part. It's just more like, because micelles, this whole process is kind of interesting. And this really is what ties organic chemistry to biochemistry, is the fact that we can explain with hydrophobic and hydrophilic regions why a micelle works naturally and why it would be a good place for RNA to be hidden so it doesn't get degraded by the environment. And if you take that further, you get a phospholipid bilayer. Phospholipid bilayer is the same sort of amphiphilic molecule, except that it's set up to be double layered instead. So instead of one tiny micelle,
But for that, like, I don't know, whenever we do it in biology, it's like two coming off of the one, right?
correct, because it's basically, it's this molecule.
Oh, okay.
If you take this and replace it with a phosphate.
Okay.
So
And this is phosphate.
the phosphate is the hydrophilic piece, and these two chains are the hydrophobic piece. So this is the simplest form, but this is a little bit bigger and easier to take something that already exists in your cells and turn it into those as well. And you get twice as much hydrophobicity. That actually is a word.
Okay, I believe you.
And so all of this was a digression just because, as an example of biological applications of an ester being turned into an acid or vice versa. Either of you ever watched the movie Fight Club?
Yeah. What? Yes.
It was a required viewing for 20-year-olds when I was in college. It's that time period. And they actually do describe this when they're talking about making soap. They talk about taking triglycerides, fat, exposing it to a strong acid, and making soap with it. And then they take their whole purpose was to then take the glycerin and make nitroglycerin, and they hand wave that part. But they actually did do the science properly-ish for the making soap piece.
Wow.
What they do is it's like, okay, then you have glycerin. Then you just add nitric acid to the nitroglycerin, the glycerin to make nitroglycerin, which is right. Finding concentrated nitric acid is not as easy as they make it seem.
Yeah.
All right, so let's do some practice.
What? You do know all of this. I don't remember it. I was a little preoccupied this weekend. Trying to reach my grandparents. I can't help. Where did you see it? This is. And what it does, so what is it under? In the title? No title. Just the reactions from like the last week. What is it? What's it? So around your notes. Get rid of the whole elemental group and just get double bonded oxygen and pH. I know it does. I believe it. Thanks. Sorry. Elemental instinct. Just live by that. Don't care about it.
Acer into methanol. Because it's gonna leave as a deprotonated alcohol, and then we expose it to water at the end.
Yeah.
We're gonna get methanol.
If we were drawing out the mechanism for something like this, would you expect us to show the byproduct?
At some point, is basically what your intermediate is gonna look like. There's the new H we added, there's the old methyl group, or the methoxy group. What this is gonna look like is this leaves as a leaving group. And you reform the carbonyl, so your intermediate is gonna look like the aldehyde. Plus the deprotonated.
Okay.
So you would show it there, and then this then gets protonated, or it gets a hydride added, so we get finished. Except
Oh, it adds the R.
it has to be hard, which is manifold.
It puts the R, right?
On the carbonyl carbon. And then again, we also have plus.
B.
Yeah.
Great.
I just drew it down here so there's more room.
You. Able to make others. Oh, because you added methyl.
Yeah, what color code?
It's just a period, but it's not only one extra. I was really preoccupied this weekend. We didn't have homework.
No,
I would not. We told that.
no, your homework was help with senior day. And you did admirably.
And then I helped seniors. Oh my gosh.
Help seniors.
I was nonstop walking. I was like back and forth, back and forth, back and forth. I love my grandparents when they're like herding cats because I'm gonna say she goes fast from point A to point B. She can't slow down. Pop was hit, he goes slow in his cane and he sees sights and he makes friends with everyone. By the time I was my 10 grandma's gone. By the time my grandma and Pop was gone and promised like 10 more people love a cello and missing and I just think about air sights. That was my home.
My mother-in-law is coming for this coming weekend on her own. And she's not old, but she also doesn't travel on her own very often. And is going to be staying with us for the weekend, so.
Your father-in-law will survive. Every time anything happens, my grandparents, even if grandma isn't there, he goes, "Carol." That's because it's her fault.
Laura's dad knows everybody on the lake where they live, and so he'll be fine.
Yeah.
He'll probably have 3 different sets of relatives stopping and bringing food. Because it's the Midwest.
Okay. I got it, I know, I don't even feel bad, you know, I just laugh at it. I think in this case, the recording, but the word. I mean. That didn't make sense, that's not, but the ring will open, you just take rid of all double bonds and replace these. I was closer, the one I was closer to the wage, you were not closer, that's. Why is that?
It's the same thing we just did here. Or sorry, that we did here.
Yes.
We went over the methanol and another alcohol, except that they both happen to be on the same carbon chain. So this is the oxygen that was right here,
Yes.
and this is the oxygen that was the carbon.
Rather than still no breaking. I never said it, I said, opens the ring. In this case.
It broke that high bond and that bond there.
Right, it like it's rid of the double bond, I don't know, the way she said it. Well, I said that it didn't make sense. I think that. Well, I did.
Welcome to being a little sibling, where even when you're right and wrong.
It's been her whole life.
All right, so what if we just have water and acid?
I don't like it. It's the easiest one, but I don't like it.
So it's acidic conditions. This is a good one to draw our.
Acid condensation hydration. Great, but it's mark. And
It's not hydration. It looks kind of like the hydration from aldehydes and ketones, except we have a good leaving group. So what happens first is you protonate.
yeah, the mechanism of the exam with this one, I definitely, I saw it and I was like. You know, I was kind of guessing for most of my tries anyways, and I was like, well, I made it from point A to point B, so I have to be doing something right.
You were, if all your steps make sense, then I can give you a lot of partial credit there. So first step is just with protein and carbonate, because we're under acidic conditions.
Right.
But then we have water around.
Okay.
And we get a tetrahedral intermediate.
Okay.
I was about to sneeze.
Okay. Let's try. I was certain don't pass out. Not prepared.
More don't sneeze because my hands are full.
Mm.
So we get this intermediate that looks like there's our ethyl group. And all of these steps, if I was being really careful, are equilibrium. Because it's all reversible if we change concentrations. Right, because then what we have is we're going to do 2 proton transfer steps at the same time. Remember, acidic conditions, we can't have this leave just as an ethoxy ion. You can't have a negative charge on the leaving group.
Right.
So we have to protonate it first. So we might as well deprotonate our water at the same time.
Oh, where did that come from?
We just did 2 proton transfer steps at the same time so that we can save ourselves a step of drawing.
That's fine.
In the interest of board space, once you have this written down, I'm just going to erase.
I have all of it.
Beautiful. So then our. So this is what we have
With equilibrium arrows.
with equilibrium arrows.
Since when did we start introducing those? I feel like it just popped up one day and we just went with it.
In Gen Chem.
No. In OChem, they
In OChem.
popped up and we just like,
We talked about them all the way back in first quarter. Like, okay, it's irreversible versus reversible.
and then they went away. And then all of a sudden we just like saw it and just flew with it and didn't question it.
It's basically, we take care to draw the equilibrium arrows anytime the reaction can happen either direction. So especially if it's all it takes to change in concentration, like we can do a dehydration reaction, elimination reaction versus the hydration reaction. Both of those can occur, but they have to be substantially different conditions for that to happen. Versus this is fairly different conditions. All we have to do is change concentrations and we can get this to shift back and forth.
Well, and like when we're drawing our mechanisms, I don't, we haven't really went into when we put those in.
On mechanisms, I'm not gonna get picky. I just want you to understand this reaction happened both ways. And based on the way I drew it, we have our blue oxygen is the one that reformed the carbonyl, but I could have just easily taken this one and reformed carbonyl. Plus our ethanol. Then one last proton transfer step to deprotonate this. So our final product is just the cyclohexane carboxylic acid. And ethanol. So all this reaction does, the net result is we take the ester and we turn it to carboxylic acid. It's a lot of steps to show for that. Most of them are just proton transfer steps though. Basically, okay, one step that's not a proton that's really significant is nucleophile attacks and then reforming the carbonyl when you're leaving group leaves. And all of these carboxylic acid derivative reactions are going to have the same steps. Those ones are the ones that don't change. And I did not put that summary slide on there, so I'll pull that one up in a second.
I'm still a little done with that.
Now I think it actually. I mowed my lawn on Sunday, and it was. I was so stuffy after that.
I take out the pools every day. But I was sick last week really bad. And then I traveled while I was only like 9% better. So then like I literally brought a box of tickets in my car because I was like blowing my nose. So like how did my nose produce this much? How was it hiding in my nose?
They,
In there.
Again, I believe this is tear gas rather than pressure, but I believe tear gas actually stimulates the production of mucus. So in addition to causing crying, which the medical term is lacrimation, lacrima in Latin means tear. It also causes your nose to just run incessantly. So when people have to do the like get tear gas before you can ever be in a situation where you might use tear gas, they basically just give you a bucket and you just have to sit there and your face just drips into the bucket for a good long while. Okay, so what's gonna happen? Even if this one, if you take a carboxylic acid and you put it with hydroxide, what's gonna happen?
It's gonna rearrange the.
Well, it already has an OH, so we're not gonna convert it to an ester or anything.
No, don't you replace it with the.
Close. So let's think about what the steps are. You put a strong base with a weak acid. What does a strong base do to a weak acid? Say that again.
Non-acidic.
Close. It neutralizes it, right? Your strong base is going to deprotonate the acid. So from benzoic acid, we just go to benzoate. The only thing we ever really do with these alkyl halides is their target for a nucleophile, right? Nucleophile. So do we kick off the hydrogen or the iodine? So this one I don't think we actually went over in detail yet, but this is a logical step that we've seen from the other side. When we first studied these, we said, oh, and a deprotonated acid can be a nucleophile. So we're just going to wind up with so we can make an ester that way too, by using an acid as a nucleophile.
What's the thing that you guys access and not that?
If it doesn't say excess, then that usually means you need a 1-to-1 stoichiometric ratio. So for every mole of the ester in D, you need 1 mole of acid and water in theory. A lot of these we would have excess though, even if we don't list it. For these ones, if it says excess, that usually means it's happening twice, or the second molecule has to be there to neutralize something. So in this case, it's another excess one, because this is going to get reduced twice.
So both of them become H's?
Correct. So you're going to start, the first step is you're going to break that one. And get an intermediate that looks like this. So this still deprotonated because we haven't added the water yet. And then we're going to reduce this carbon again. Sorry, so second intermediate looks like that. Then step 2 is just reducing a proton equal to this. So your final product. Just looks like that.
Why are you adding it? Why don't we have the?
Oh, sorry. I was thinking that that was lithium aluminum hydride. You're absolutely right. And let's color code again. So we're adding the ethyl there. So our first intermediate would look like that.
But we keep the OH too.
We keep the OH. I just rearranged it so it was a little bit neater.
It's getting real cool.
Yep. All right. So
Why do we have both metals in the same spot?
because this is the carbon that is the most oxidized, so this is the carbon that's going to get reduced. This carbon, once it's right here, we can't reduce a primary alcohol with Grignard reagents or lithium aluminum hydride. We can reduce carbonyl stuff. So our target for any of these or these is going to be the carbonyl carbon that needs to get reduced.
Or pecan?
Probably not. Okay, so I'm sick today, so I'm gonna go home and trade off with Laura. So thank you for moving lab. Or I assume you two were together since you're both emailing me at the same time. Okay.
And I was like, do I need to come home early on this
No. So we'll talk about that in.
I was thinking not day anyways, but I was like.
And then it's Dash's last regular season baseball game today, and I have board meeting today. So there's still undefeated. It's very, very busy day.
Yes.
I would assume Carl was coming.
I think so. Well, I don't know who has the chillers. Maybe like them.
Their oldest is 13. He can take care of them. Yeah, his kids are pretty great. Theo. Laura refers to Theo as her spirit animal. Theo gets done things he just leaves.
Good for him.
All right, so we covered this the other day, but I wanted to recap. So if we know this,
Yes.
anything left can be turned into anything on the right really easily. Right, by just having the right nucleophile. So the question is, how do we make our acid chloride? Because as long as we can do that, everything else falls into place. It gets really easy. So this is our reaction for making an acid chloride. You start from the acid, you expose it to thionyl chloride, SOCl2. The net result of that is you make an HCl molecule and an SO2, which is a gas. Which, remember, a lot of people write it like that, meaning that it leaves the system, which helps with equilibrium too, right?
Yes.
And our mechanism is actually really similar to what we've been seeing for the others. Right, so we wind up with the first step though is the pi bond attacks the sulfur. We kind of rearrange things a little bit so that the other carbon turns into a carbonyl. It's protonated now, but that's okay because we're under acidic conditions. And then the sulfur group, the sulfur to oxygen is more stable bond than sulfur to chlorine. So sulfur to oxygen is going to kick off the chlorine. And now we make this group right here is a really good leaving group, even better than a chloride.
If you were to draw it all on one arrow, it would be the sulfur with its things and nothing else. Like no water.
Correct, in this case. The chloride that we're going to wind up adding here actually comes from the sulfur,
Right.
from the thionyl-chloride. So all this is, if this was stable enough that we could easily isolate it, this is another acid derivative. It's just so reactive that we don't ever really see it stop. So going back to that other slide that had all of them listed by their reactivity, this one would be off the chart to the left, right?
Okay.
So but we can make something super reactive by starting with the cyanyl chloride, and then we just let the chlorine that was right there come in and bump off this. This is our excellent leaving group, right?
Yes.
So our chloride is just going to come in. This is the same step that we've seen for all, or the same two steps we saw for all of the other acid derivative reactions. Nucleophile attack and temporarily break the carbonyl. Leaving group leaves and you reform the carbonyl.
Yeah.
So let's do more practice. Some of these we haven't seen yet. In fact, actually, I'm going to come back to this. Too many of these we haven't seen. Dibond
Yep.
is a single hydride source. We're going to come back to that in a second, though. In fact, hang on. I left off some slides. Maybe I didn't save the version I was working on because I'm missing some slides that I wanted to put on there. So, the very least.
Did we take breaks?
Sure. Yeah, let's take our break. Let's come back at 5 till.
Okay, will you post it or at least post?
I'll post the updated versions. Yeah.
What's this? That's what I want to get besides the little dog out. There's no have to wait. But I don't know. I didn't see that though. Ask. I created the there usually. Very different.
So all I added was this slide and then back before, right after this one, put this other summary. This is our general mechanism pattern. This is the one that I was looking for earlier. Where it's nucleophilic attack and loss of the leaving group, and you reform the carbonyl chips with some proton transfers potentially scattered in there as well, depending on acidic versus basic. All right, so this was the last thing we covered the other on 2 weeks ago. Lithium aluminum hydride and our greener reagents can't stop halfway. So that's why they're always shown with excess. When we have an acid hydride or an acid derivative being produced, because they can't stop halfway without leading to my favorite quote from the textbook, simply leading to a mess of products. Right, so if we want to stop after one reduction step, we have 2 tools to do that. I just overrode the existing title. So you should be able to see it in the same link that it was. It should look identical. Mine shows the updated version there. Well, but not that one. So close out of that one. Go back. Okay, it is up there. This is one of the only ones that have notes. If you want to just take notes on this one, and it might just need a chance to refresh. All right. So if you want to do a single step reduction where we're adding carbon, so to go from any acid derivative to a ketone and stop there, we use a Gilman reagent. And Gilman reagent has this copper lithium piece to it. And the R group, the red one, the red part, can be any R. So just like with a Grignard reagent, this will function identically to a Grignard reagent, except it'll stop after one step. It'll reduce an acid derivative, but it won't reduce a ketone or an alkaline.
So this is after, before the review. Huh? The slide before this. Oh, it is this? Oh, I'm sorry.
No worries. Was the thionyl chloride slide. Once you get it to a ketone, though, now we could use a Grignard reagent or lithium hydride to finish it. So what these allow us to do is to add 2 different things when we're doing our reduction. Instead of adding, like we added 2 ethyl groups on the previous slides, instead of adding 2 ethyl groups that have to be the same, we could add a methyl and then an ethyl. Or we could add an ethyl and then a hydride. So it allows us to mix and match. So it's really, really versatile now. The hydride equivalent is this lithium trialkoxy aluminum hydride. It gets written like this, or DIBOS. DIBOS stands for diisobutyl aluminum hydride. And an isobutyl group looks like this. So it's still an aluminum hydride. It's just a specific aluminum hydride that, because of this big bulky group, or these two big bulky groups, will only have one hydride. And so you can do the single step reduction. All right, so both of these mean the same thing. All right, so this will take an acid derivative. Either of these will take an acid derivative and turn it to an aldehyde. And then we can use a Grignard reagent if we want it to go as things attached to it. All right, so this is another mix and match option. The other thing I want to talk about before we do that practice, that flat level practice, is that SOCl2, if we expose it to an acid, gives us the acid chloride. If we expose it to an amide, it goes through a similar mechanism, but it doesn't take us to the acid chloride because the nitrogen is not as good of a leaving group as an oxygen is. So this first step looks really similar. Pi bond attacks the sulfur. We wind up forming a double bond from a lone pair. And then we kick off a chloride. So this first step in this first intermediate is identical to what we would get with an acid. Thing is, instead of then having an acid or having something come in and kick off our SO2Cl, our base is just going to take a hydrogen off. And we wind up forming a carbon nitrogen triple bond. So the result of this is a way to turn an amide into a nitride, which is that carbon nitrogen triple bond. So now we have everything we need to do this slide. Let's do more practice.
We'll get rid of which.
You can write the plus H over not. It's we're showing you. I've also broke it apart. You might as well show the water here. That's after step one. And then we expose an acid chloride to an amine, to a nitrogen. So this is our nucleophile now. And the chloride is our leaving group. So we're going to kick off the chlorine and replace it with the nitrogen that has two metals. So we make it amide. And whatever is attached to the nitrogen stays attached because our carbon's not good leaving group, so we're not going to take the carbons off.
CH2.
Sorry, I just miswrote that. That was one we just went over. So the carbonyl carbon stays there, but it becomes sp hybridized. We've made a triple bond to the nitrogen.
And then the chloride, that makes me. Well, what are probably 70
This is an acid chloride written in condensed form.
Okay.
So acid chloride, first off, this after step one, this is going to turn into the acid. I'm bringing it over to that far side, so I have room. So after step one, we have this. Now an acid gets exposed to an acid chloride.
Yeah.
And pyridine is a base. So now we have this
Okay.
reacting with this. In the two steps, but I'm just showing it quickly. So we're going to make an anhydride. If you let an acid chloride react with a deprotonated acid, this now attaches to the carbonyl carbon. And we're going to get right, because any of those other acid derivatives start from the acid chloride anything that can act as a nucleophile can replace that chloride. This whole thing is our nucleophile. So it gets added on to wherever the acid chloride is. So that's our aluminum hydride that only reduces it one step. So it takes any acid derivative and turns it into an aldehyde. And then whatever, in this case, the methoxy group is just going to get turned into methanol. Just like we saw before, right? All right, I'm going to give you a few minutes on the last three because they're all just converting into from a reactive acid derivative, that's the word, to a less reactive one. So we're just converting from one acid derivative to another. So try and draw them. I'll give you a few minutes head start. And again, I'm being sloppy, not showing all the proton transfers steps, but just so we can track what's getting to where.
Yep.
Now we have a big amine reacting with an acid chloride. Doesn't matter what's attached to the amine, as long as it's still got one hydrogen. Speaking of allergies, this is Benadryl.
Benadryl makes me out.
It's also, if you those ZQuil supplements, stuff like that, the over-the-counter sleep aids. If it's not melatonin, most of the time it's diphenhydramine.
Okay.
Actually, now I'm second guessing myself. Diphenhydramine is. I was wrong. Sorry. Diphenhydramine looks like this. That's Benadryl. This is diphenylamine, not diphenhydramine. So I take it back. Close. But if you look at the price on a giant bottle of Benadryl versus the sleep aids,
Yeah.
you're paying a whole lot more per pill. So never buy the ZQuil. You need the sleep aids, just buy Benadryl.
Yeah. Good to know. I usually put the children. So. Maybe we don't sleep stuff.
That used to be the back in the 80s and 90s, that was the accepted form of going on a road trip. If you needed to go fast, was put some Benadryl in the Sprite and give it to the kids.
Yep.
Accepted might be the wrong term, but common.
Yeah, yeah.
All right, last one.
Yes.
So it's just acid and water. So we're just gonna break that.
Where did that? Oh, from the bottom.
We added water to it. It's basically just an acid catalyzed hydration reaction.
But we left the dump one.
We left the double bond, but we turned an ester into an acid and an alcohol. So just like that triglyceride example we looked at the beginning of class, we got into the weeds about myself and that amphiphilic and things like that, but that was the same reaction that was happening. So if you take an ester and you expose it to H3O plus, you're going to get the acid and an alcohol. All right, so we basically have we really only have two different things that we do with the acid derivatives. We convert from one acid derivative to another acid derivative, or we reduce the acid derivatives. And the way we reduce them, we have a couple options. But that's going to be our big picture way to think about the acid derivatives. Either converting to another acid derivative or I'm reducing it. There it is. All right, so the other reaction for nitriles, if we're trying to make a nitrile, is one we've seen before. We can just use cyanide as a nucleophile if we have a good leading curve, which does add a carbon there as well. Right, because the nitriles were sort of our odd one out of our acid derivatives. They have the same oxidation state as our other as the acid derivatives, but they don't have a good leaving group attached. So since they don't have a good leaving group attached, they react a little bit differently. Right, so if we try and do some of the same reactions with nitriles that we do with other acid derivatives, if we just add H3O plus and heat to a nitrile, we can turn it back to being an amide. And amides are the most stable acid derivatives, but if we add enough heat and we play with the concentrations enough, we can get that turned back to an acid as well. It's not going to have great yields, but it's doable. And if you have enough water and you're making ammonia, if you heat ammonia, it makes ammonia gas, then evaporates off faster than water does. So you can basically use Le Chatelier's to get back here from a nitrile, even though it's not great yield. The other way we can do it is we can just oxidize it and go from a nitrile. If we do this under basic conditions, we can go straight to the acid with better yields. So this is actually a better option for the most part. And once we get back to an acid, we can take this all the way back to an acid chloride with SOCl2. Right, so all of this is one big merry-go-round where we can kind of go in as many circles as we want as long as we don't run out of our product or reactant. If we take a nitrile and we expose it to a Grignard reagent, we can reduce it to making this nitrogen-carbon double bonds, which if you then expose that to acid, and there's water around as part of the Grignard reaction, we can turn it to a ketone as well. So going from a nitrile to a ketone is 2 steps, but you can use Grignard reagents to do that too. And last but not least, if you wanted to just do this straight ahead, full on reduction with lithium aluminum hydride, we just turn it all the way to an amine. Just a nitrogen single bond to a carbon. Right, so these look a little bit different, but they're all pretty similar reactions to what we've seen before. But the reason they look a little bit different is because it's a nitrile instead of a typical acid. And instead of ending with an alcohol when we reduce our acid derivative, it's a nitrile, it's a nitrogen. So the nitrogen equivalent to an alcohol is these. We can actually look at the mechanism or hydrolysis of the nitrile too, because it does make sense. There's a partial negative with a lone pair here that we can protonate. Once we protonate it, that means this carbon is a good target for a nucleophile, even a weak nucleophile. So now we end up with, we get this intermediate that kind of looks like a bizarro world amide, where the double bond is to the nitrogen instead of the oxygen, but it's not going to stay that way. It's going to rearrange itself. And we're going to protonate the nitrogen again. And so once we do that, then it's just, we have a resonance structure, we just do some more proton transfer. If you look at this, it's all proton transfers, other than one nucleophilic attack. And then we're just moving some electrons around.
Like whenever H3O is involved, it's typically just like a lot of.
Yeah. So before we do some more practice problems, are you two familiar with the Lego ideas? Lego ideas are basically you can propose a Lego set, and if you get enough people to sign a petition, Lego will review it and might actually make it.
Okay.
There's one right now that is a biomedical institute
Aww.
with little pipettes and instruments and microscopes. But they just look like syringes, but.
Oh my god. How do we say yes?
I'll put the link in, you have to sign up for Lego Ideas account, but basically then you can just like click support.
Okay.
And if they get to 10,000 signatures, they're at about 5,000 right now. They have about 200 days to make it to 10,000 signatures, and then they get a formal review by the panel.
That'd be so cute.
I know, I think they're pretty awesome.
Oh my gosh.
They even have like chemical storage and
Yeah.
beakers and cell cultures.
It's so cute. I was at Target, there's a Lego like Polaroid camera, like that.
Those are cool. Probably cheaper than actual Polaroid camera. Yeah. All right. More practice. Excess lithium aluminum hydride. Carbonamide. That's it for that one. So just like the nitrile or the amide, when you expose it to excess lithium aluminum hydride, you get the you basically fully reduce it as far as it will go.
Oh my god, makes sense. The Polaroid. But I didn't want to go.
Yes,
Left it that,
I did. Luckily, Scott grabbed it. And that's.
I gave it to Scott, it's your office.
There you go.
And we have your pyramid too.
Yeah, I grabbed both of those. Thanks.
he laughed at the I'm like, no, he brought this up, like. Yeah, it was on his show. Yeah.
I could always produce another one, but I've already made one.
Too.
Yeah, so this is our nucleophile. It's gonna come in here, and that gets kicked off. But then, if we just left it like that,
Oh, right,
and we're not gonna leave it like that, so it's proton transfer.
with more ending street. Or,
But yeah, so, and actually what we'll see first, because this is basic conditions, right? I mean, our ammonia is a weak base. So we'll actually see a quick proton transfer. Like this. Maybe NH2. With a negative charge, just because that's under basic conditions, we're not gonna make anything with a positive charge,
we
right?
did that first. Or attachment, or,
Well, I guess we can't make any strong bases, and NH3 is not a strong base, so I guess we could leave it like that. The general, to be safe, the way to do it is under basic conditions, don't let anything have a positive charge. But in this case, I would make an exception to that because we're not making a strong acid, we're making a weak acid, which then will go through the proton transfer. So your intermediate would look like this. And then we would see a proton transfer step to make an NH2. And then this reforms to get us our final product. All right, amide plus H3O plus in heat.
it replaces the NH2 with H, right?
Yep.
That, where the packet notes, that we just did. And, we'll- right here. Don't look at myself. So we did, we started here. Picture.
What do we get when we reduce the nitron?
Just did it, didn't we?
We did.
It. Distributed for.
Correct. Just be careful that you don't forget that's still a part of it. Like I almost did, and put the nitrogen there, count your carbons.
Yes.
Yep. If we scoot backward 1, 2.
Is that the 10% or is that?
No, this is just after step 1. Right, so we start by making this weird nitrogen looking thing. But then because there's water around, it always is just going to rearrange itself into, so we added a methyl here. This made our weird nitrogen equivalent to the carbonyl, which then just gets replaced with an oxygen. So we made a ketone.
And that's after step 2.
That's after step 3. So after all of it. So nitriles can go through a single step reduction to stop the carbonate. So what do we get after steps 1 and 2 for C?
I don't have to see.
So that's after step 2. All right, we add the R group to our nitrile carbon, and then we turn the nitrogen into a carbonyl. So then now we just have a ketone, and ketones with lithium aluminum hydride just turn into the alcohol. Nitrile plus H2O plus some heat will turn into an amide first, and then into a carboxylic acid. Keep pushing on it. So our first product looks like this. And if you keep adding heat in H3O plus, we get the acid. So acids, amides, and esters all can be converted in between back and forth pretty readily by just messing with concentrations. Acid chlorides and acid anhydrides, because they're so much less stable, take a little bit more finesse. But those esters, acids, amides, pretty easy to switch them all back and forth just with hydrolysis reactions, just with water and acid, or alcohol and acid, or amine and acid. Who wants a reaction summary slide?
I do. Synthesis of what?
Anything.
Of the things we've talked about today. Right?
Basically, so we can go
Which is the amines and nitriles.
amides, nitriles, acid chlorides, acid anhydrides, esters. You can even get in there to aldehydes, ketones, and alcohols to some extent. So we have this whole sort of ecosystem of reactions for acid derivatives, which are also connected to our other reactions because we can make aldehydes or we can make ketones or we can make alcohols. So if we're thinking about this like it's one big subway system, this is one of our big transfer hubs, as are aldehydes, as are alcohols. Then this would have, there'd be a whole nother reaction somewhere that look kind of like this for the alcohols or aldehydes. And so they're all connected together. This is just a convenient way of referencing what things do I need, what reagents do I need. Because once we can get here, we can get to anything else on here.
Where?
Well, from anywhere, we can get anywhere else on here, right? You follow your arrows. There's not, doesn't mean all routes are equal. There are some that are better.
And these all have names. Right?
I'm sure they do. I would be less concerned with you knowing what the reactions are called than just knowing that, okay, out of my acid derivatives reactions, I can get back and forth between any of them. Like if I'm trying to go from an acid chloride to an amide, I'm not going to stop. I'm not going to take this route, right? I'm going to take the express route that skips all the intermediates because that's going to give me a better yield. So that's what I mean by not all routes are equal. They're all valid. That doesn't mean they're each the best choice for the situation. You still need to have some discretion to figure out which one is going to make most sense. All right. Should we either take a quick break or we can talk about the research project for 10 or 15 minutes and be done for the day? Do you want to take a break before we do that or should we push through? It's attached. Let me pull up the So lab today is going to be you looking for your research project articles. And they're under the assignments tab. So your first assignment here, the way that the due dates are set is not next week, but the week after. We're going to have a meeting. Our lab that day is basically meet with me and talk about your 4 potential papers. And then the end of the week, so this due date is actually Monday at midnight. So I want you to find all 4 of your papers so that you can come talk to me on Tuesday. And then by the end of the week, pick one.
Okay.
And then we'll do your presentations. I didn't double check that date. I think I'll ignore the June 16th because I need to calendar or we set that. All right, so.
But we're presenting to. So which one?
I still have to think about that too. Maybe to Carl's class, but probably we'll find somebody for you to present to.
If we do Carl's class, and we both took like 5 minutes to just do a quick presentation, it wouldn't take too long for it to come out.
Yeah, I got to see if Carl has. It wouldn't take that long, but the research project presentations are always a long day anyway. They always go over, and so adding you two each doing a presentation.
That's true.
So I have to think about that still.
Okay.
But I'll try to have more than just the 3 of us in the room.
Yeah, because we'll already be talking about it together. So
Right. Right.
Yeah.
All right, so the assignment that you're starting today for your 4 potential articles is So here's what you're gonna turn in for 4 peer-reviewed journal articles related to organic chemistry in some way. It can be just a little bit related, it can be like directly open. But I want to know what's the title in the journal where it was published, the article abstract, concepts from, and then a list of what concepts from our class are in the article are relevant. And then why you think it's interesting. And I actually think I'm going to make this due next Friday, not the Monday night. Because the other thing that you'll be able to do is you probably won't have access to the full article at this point. But if you submit it on Friday, I can give you PDFs of all 4 of yours for you to go look at. And that way you can have the weekend to look over them before we have our meeting on Tuesday.
Yeah.
Right. So we'll do that instead. And I'll change the due date. Okay. Let's just do that right now. All right, so I gave you some links. The Nature is always good, but Journal of American Chemical Society, or the ACS, they call it their flagship journal, it's just called JACS, is going to be like the Journal of Organic Chemistry is affiliated with this, is on the list of associated journals. And so anything from that journal is going to be fine. If it got published in the Journal of Organic Chemistry, that's a good option.
Yeah.
But then there's going to be lots of other ones. Nature articles are typically it's a big deal to get published in Nature. That's probably the premier journal that you can get published in. It's either Science or Nature.
Okay.
Nature is more active these days. And so they're typically written at a higher level, not meaning more complicated. They're written so it's easier to understand because all scientists, including psychologists, read Nature. So if you're writing an OChem article for a psychologist to follow along with, you're not going to be as deep in details.
Yeah.
So Nature articles and JACS articles are going to probably be the easiest to read.
Okay.
But they might not be as specific to what you want to talk about. So
Right.
That's why I gave you a list of other subjects and other journals that you can look through as well. And hang on one second. They're usually pretty busy, but either the last author or the first author, if you just email them and ask them for a copy, the authors don't get like a kickback based on how many times this article gets downloaded or anything's not like YouTube. They're very happy usually to just send you a PDF of the article. So you can always just reach out and send an email if you need to. If Sci-Hub doesn't have it and I can't get you access.
Yeah.
It's always because the people that are spending their lives working on this stuff want other people to be interested.
Yeah.
So they're more than willing to just send you a copy usually. But for this assignment, you're just going to submit the abstract. The abstracts and the title are fine, no matter, or you should be able to find those without being behind a paywall.
Right.
So you send that, and actually let's add, I'm going to say add the DOI link
Okay.
so that I can find them easily too. Make sure I'm getting the right one. All right, so that's all this week's lab assignment is. Next week we'll have another lab assignment. It'll be a paper assignment. We're going to talk about 2D NMR. but I wanted you to start thinking about this, and you have, you know, the rest of the day today, and the rest of the week to work on too. And you can talk to me about it along the way too. If you have 10 that you find, or this one seems really cool, but I'm worried it's too complicated for me to understand, or not. Like, we can do some of those conversations too, before you actually submit it, but you should have a couple good articles in there, and then maybe a couple that are less likely, but you seem really interesting, or something like that. That we'll be able to talk about next week.
Okay.
All right, so any questions on your lab assignment?
I don't think so.
Cool.
But we don't, are we meeting for one?
Nope,
We just did.
we just did. That was lab.